Hello, everybody. We're going to introduce a new topic today called electronegativity, and it was generated by one of the most famous chemists ever. So, the questions are: electronegativity explains charges in bonding. What does the electronegativity concept mean? That was proposed by Linus Pauling. What does the electronegativity score tell us about an element's bonding? EN, capital E, capital N, is the abbreviation for electronegativity. What elements have the highest electronegativity score and which the lowest? 4. When two elements combine, how do we use their electronegativity scores to figure something out? 5. What does polarity of a bond mean? Why does polarity of an element in a bond matter? And 7, what's the partial charge in a covalent bond? All right, so partial charge is a vocabulary word, isn't it? And what is the symbol for a partial charge? So those are the essential questions we're going to be working on. And it begins with Linus Pauling. He was born just at the turn of the 20th century. He was an American theoretical physical chemist. So he was a chemist. But he's the only person who's ever won 2 unshared Nobel Prizes, meaning a lot of times 2 or 3 people win the Nobel Prize, but his were individual prizes, both of them. His first prize in the early 50s was awarded for research into the nature of the chemical bond, which is why it's so important to us, because we're studying chemical bonding. And he also used it, how do you figure out molecular structure? All right, that was very important because it was hard to figure out structures then. The second he won in 1962 was especially amazing. He was recognized for his efforts to ban the testing of nuclear weapons. So he was so horrified after the bombing of Nagasaki and Hiroshima in Japan at the end of the World War, that he wanted to ban the testing of nuclear weapons, period, and then have no nuclear weapons. All right, he wasn't opposed to nuclear power for electricity, but he was opposed to nuclear weapons. All right, so he became very well known. He also became very well known for espousing that vitamin C would cure the common cold. So most of us who get a cold also take a lot of vitamin C as a help, but it's never been recognized as a way to cure the common cold. All right, so if you want to read more about Linus Pauling, you could go to Britannia. Now, I just want to say something very special. All right, so this is the breakfast table. All right, and this was Linus Pauling. All right, I'm setting the stage. It's in Ventura, California. In I don't know for sure what it was. I think it was 1991. All right, and then over here was sitting here with her legs under the table, was a chemistry teacher who had come from Iowa just to have a chance to talk about science education, and her name was Janet Robinson. All right, I had no idea that I was going to have a chance to meet the great Linus Pauling, who was just about the most famous Nobel Prize winner that I knew of. All right, but I did. And it's because my roommate was a University of California, Berkeley professor, and asked me if I wanted to meet him. And of course I did. So we ate breakfast together and talked about science education. It was amazing. And of course, especially chemistry education. Amazing. So it's one of the key events, professional events in my life. All right. But he's not important because I met him. He's important because he's important. All right. So, electronegativity is a measure of the tendency of any atom to attract a bonding pair of electrons. So remember how we've talked about these electrons in a covalent bond. The Pauling scale is the most commonly used. A bonding pair of electrons, remember, is a covalent bond. However, we'll notice as we go down, it also says something about ionic bonds. So this is the table that was created by Pauling. So we can look at first over here. So we see that hydrogen is a nonmetal, all right? So he's different from the other guys on his block. Let's look at the rest of the metals. So if you look, all the alkali metals are around 1 or a little less, with cesium and francium being at 0.7. So they're the lowest in that row. When you look at the next column, some of them are 1.5, etc. So it turns out that these two have the lowest electronegativity. Lowest. And remember I said En meant electronegativity. And we could call them a numerical value or a score. So Linus Pauling figured out, based on the properties of an atom that we've talked about, how far the valence electrons were from the nucleus. All right, indicates their tendency to attract electrons that are going by. Remember we talked about that? And that some, like these guys over here, the valence electrons were far away from the nucleus. So they had not much attraction for a pair of electrons. All right, so nuclear charge is too weak. The nuclear positive charge was too weak. So I expect that you're taking notes on this sheet. Half of your screen is the video, half of your screen is this assignment, so you can take notes. The nuclear positive charge, all right, is so far away that it doesn't attract a pair of electrons easily at all. So metals have low numbers, it looks like. And so let's just pick this. All right, aluminum 1.5, the highest one is over here at 1.9 for a metal. All right, so metals are pretty much 0.7 to 1.7. All right, so these are low electronegativity scores. Now, let's look at the opposite, which are these guys right here, the nonmetals. So, the noble gases, remember, hello, pretty well. He's not alert, but he's breathing well. All right, so look at nonmetals now and see if you can find the range for them yourself, just like I did with metals. All right, we might be interrupted a little because there's a respiratory tech in here helping my husband with his breathing. So, when you got over here to the nonmetals, did you notice if we discount the noble gases because they don't bond with anybody, we see, 2.5, 3, 3.5. Oh my gosh, look at that. 4.0, a lot higher than the metals. And then there is nobody higher than that. All right. So this one, remember, has a high nuclear charge. And he only has 2 energy levels. So fluorine is really an attractor of electrons, all right, and an electron pair. All right, so that would mean that his electronegativity value is high because he's very attracted to a pair of electrons. Whereas among the rest of these, all right, it's pretty low. I'm sorry, I marked them out. But the most important one's carbon, 2.5. And then we see that oxygen and chlorine are below, and next to fluorine, oxygen has an electronegativity value of 3.5. So we can see that if this is fluorine with a +9 charge, see how only this far out to this distance means that there's a lot of positive charge close to the surface of the atom. So electrons going by are attracted to this, or this is pulling electrons in. So that's why fluorine has the highest electronegativity value. It really wants the electron pair. When we look below to chlorine and next door to oxygen, we find out that the highest is oxygen, 3.5. Just 0.5 less than fluorine, and next to it is nitrogen with 3.0. We look below fluorine and find that chlorine is also very electronegative, 3.0. And we see the rest of the halogens are less negative as we go down the row. Okay, so did you find the range pretty much to be 4 was the very highest for these non-metals? And really, 2, 2.4, yeah, there's really nobody more. More like 2.2 is about the lowest electronegativity value, and those were for astatine down here, and phosphorus is just 2.1. So even is the least negative. All right, I guess I could put 2.1 here instead. Let's do that. All right, so you see how I'm learning to understand this simply by going through and characterizing those values. And the metalloids, because they're like metals but not metals, are in between. Their ranges are in 1.5 to 2.1. All right, so the non-metals, 1.5 to 2.1. All right, now what I want you to do is fill out this chart now, and go back over here. So what I want you to do is put this chart here and what we just wrote on it, and I want you to fill in this chart, low value element with the low value and the value itself, the element that was high of the metals and its value, the highest one you saw, then for the metalloids, all right, and then for the non-metals. So let me give you a few minutes to do that, and I will turn off the video. Go. So remember, this is a lot easier to do now when we've just discussed it than trying to do it later. Another minute or so, pretty much you're translating into that table form what I was just talking about. So what is the range of the metal elements from what to what, and who is the low one? We know with the metal, we'll put cesium since it's not radioactive, whereas francium was, and it was 0.7. Now find the metal we had with the highest. And looking on that, I guess we could look at tin and lead, all right? These guys right here, and mercury, yeah. And then when we look, we're just looking at our common metals. These guys down here are, you can see, are kind of exceptions. So we'll just stick to the metals that were part of our family of ones that we learned. All right, the non-metal, figure out who was the lowest of the nonmetals, and we said it was phosphorus, right? And it was 2.1, whereas who is the highest? Which element, which nonmetal has the highest value? All right. 30 more seconds. So what Linus Pauling did is take all the characteristics of the atoms, and more than the ones we've been talking about, and created an electronegativity that summarized all of those factors to give them a specific number. So he took the very complexity out of those factors and turned them into a number that we will be able to use. All right, so this is what, and his further study of chemical bonding is what gave him the Nobel Prize. So this was pretty remarkable that he was able to do this. It maybe isn't on the scale of Mendeleev in the formation of the periodic table, but it's way up there. All right, so the patterns were that the attraction that a bonding pair of electrons feels for a particular nucleus depends upon the number of protons in the nucleus, how far away the valence electrons are from the nucleus, and the amount of screening by the inner electrons. So inner electrons are those that are underneath the valence electrons. All right? So those electrons screen the nucleus from the outer electron pair and makes it less attractive. All right, so the number of protons in the nucleus increases the En. The distance from the nucleus, if distance increases, then the electronegativity goes down like the metals. If the distance is close, like fluorine, then it increases the electronegativity. And the amount of screening in the metals, especially cesium, has 6 electron rings. 5 of them are inner electrons, and they're keeping the nucleus from holding on to outermost electrons well. So they'd be terrible at grabbing an electron pair. All right, so that is the key idea involved in this. Now, let's do a comparison of the typical bonds. So, look at the covalent compounds and find out the difference in electronegativity of each of the 2 elements in the bond. So, let's talk about a nitrogen-hydrogen bond. In order to do this, we look up the electronegativity of nitrogen and hydrogen, and we subtract them. So I looked on the chart. Nitrogen's was 3.0, hydrogen's 2.1, and then, watch this, I let OneNote do this for me. I put 3.0 minus 2.1 and then an equal sign and pressed enter, and it did the calculation for me. Pretty cool, huh? So you can do that too. All right, so OneNote will do the calculation for you. So hydrogen then. Well, each hydrogen is 2.1, right? All right, 2.1. The other hydrogen, 2.1. And so what would the difference between those two be? 2.1 minus 2.1 equals 0. Yes. So there's no electronegativity difference in a diatomic element. In a diatomic, and since there's 2 of them, they're called molecules. All right? All right, now go ahead and do oxygen and hydrogen. We know that hydrogen will always be 2.1. All right. So you just need to go and find out what's oxygen's. Remember we said it was high. Carbon's. All right. So go ahead and do that now. Go up here and find out. Oh, look, here's oxygen. All right, here's carbon. So let's go back down. So oxygen, 3.5. Oh, carbon was 2.5. All right. So if we want to find out the difference, we would just put 3.5 minus 2.1 equals, enter, 1.4. All right. So that's the electronegativity difference. And this is important. That's why we're doing it. So go ahead. On the next one, we see that carbon's was 2.5. All right. 2.5 minus 2.1 equals, and then I pressed enter, 0.4. All right, you go ahead and do carbon and fluorine, hydrogen and sulfur, carbon and oxygen, and chlorine. Go. I will give you a minute to get going on these. So we want to find, oh, we know carbon is 2.5. All right. We know hydrogen in this one is 2.1. We know carbon is 2.5. And we know oxygen is 3.5. All right. So we actually know quite a bit. And we know fluorine. Fluorine right here has the highest electronegativity value. Go ahead and put that in. And then you have to look up sulfur. And then you have to look up the chlorines. So go ahead and do that. And if you remember, chlorine was another one that had a pretty high electronegativity. And then go ahead and do the calculation using OneNote. Type in the two numbers, equals, and press enter, and OneNote calculates it for you. Go ahead. So the range of these electronegativity differences we want to talk about. Okay, are you about done calculating them, looking on the chart and calculating? It's actually easier for you because you have your second page over there, right? So we know chlorine is 3.0. So we know that this is going to be zero difference, zero electronegativity difference. But the rest of them should have a difference, right? All right, so go ahead and find that difference. All right, and when you are done, I'm just going to reveal what these are over here. So 1.4 0.5, 0.4. Let's see what sulfur is. I don't want to guess too much. Yeah, it's what I thought it was. All right. So, hydrogen and sulfur, 2.1, and sulfur is 2.5. All right, that's going to be 0.4, 2.5, 3.1, 1.0, chlorine, 0. All right. So when we look at these numbers, what we find as when they are very similar, we'd say this is not polar. All right. When we talk about polar, like the North Pole and the South Pole, North Pole, South Pole, or North on a magnet and South on a magnet, we know they are opposite each other, right? So, polar means that these two have very different electronegativities. Not polar means tiny electronegativity difference. All right, so this is pretty tiny, isn't it, too? Tiny. So, not very polar. That means the two elements in it have very similar electronegativity, hydrogen and sulfur. But when we get to carbon and fluorine up here, 1.5, wow, this is very polar. This is polar. All right? This is a very polar bond. So when we use the word polar, we mean difference, and one's going one way, the other's going the other way, and we'll show what that means when we get to partial charges. All right, and this one is polar. Yeah, 1.0 is a significant polar difference. So the range went from 0 to 1.5, didn't it? We didn't have any bigger than 1.5, and the lowest was 0. All right. Now, these were covalent. Let's go see how ionic bonds differ, because even the metals have electronegativity scores. All right, the first one is the typical ionic bond, and it is sodium and chlorine. So I looked on the electronegativity list. Sodium's electronegativity 0.9. Chlorine's was 3.0, as we already knew. The difference when I did the subtraction is 2.1. The electronegativity difference. This is so polar. We call it ionic. We call it ionic, meaning ionic charges. All right, we call it ionic. So when something has an electronegativity difference that big, it means this is an ionic bond. This is an ionic bond. Ionic bond. All right, there's been a transfer of electrons. So go ahead and do these now. Cesium and fluorine. So if you remember, cesium was the smallest one. All right, let's see if we know. Oxygen, we know, was 3.5. And bromine, we don't know. So you'll have to go up and check those. All right, fluorine. Go check fluorine and barium. Whoops. Barium. Check potassium and bromine and fill in those values. Go. Do that now, please. You know the metal should be lower, right? That's what we said. So how low is potassium? How low is barium? All right. So metals. Metals. All right. Hey, here's barium. 0.9. Let me move this over a little. Potassium, 0.8. All right, let's go back down. This is 0.9. This was 0.8. Do you remember that fluorine has the highest value of 4.0? All right, and bromine is going to be less than chlorine, so it's going to be less than 3. Let's go see what bromine is. Oh, 2.8. So it's a little bit less than 3. A little bit less than 3. All right. 2.8. All right, now calculate the electronegativity differences over here. Go. Use the OneNote math ability and just type in the calculation and let it be solved by OneNote. I bet you're amazed at the size of cesium and fluorine. Yes, because look at this. We'll put the big number first. 4.0 minus 0.7. These are the highest and the lowest electronegativities of all the elements. And how did that get way down there? Let me copy it. Oh, I guess let me just do this then if it's not going to be. All right, 4.0 minus 0.7 equals 3.3. All right, so this is hugely high. All right, so this would be an ionic bond. All right, not covalent. So we know when something's going to be an ionic bond because the difference between the two elements is so great. And when you have a metal and a non-metal, like we do in ionic bonds, that's how that works. So here we have 2.6. Here we have 2. Here we have 2.6. So these are all definitely ionic bonds, right? So put those numbers in there. So pretty much then, the range of electronegativity differences that we saw in here was, this one was 2.6 and this one was 2. All right, most of them are greater than 2, right? Greater than 2 up to 3.3. For the most electronegative element and the least. So ionic bonds have huge electronegativity differences. So we could figure out whether something's ionic or not. Now, notice that these electronegativity scores are more precise than just the difference in charge. So here we're doing subtraction. So +1, let's say we're talking about sodium +1 and chlorine -1, the difference in the charges of -1 and +1, you can see down here on this little number line I did. So you could see that this is 1 to, from +1 to 0 is 1, from -1 to 0 is 1, and that adds up to 2. All right, so when you do the subtraction, +1 minus -1, you get an answer of 2. All right, so these EN scores are more precise because, 2.1, because they're including the number of energy levels and the number of protons in the nucleus, as well as the basics of that element. All right, so that's why the electronegativity difference gives us even better clue than the charge difference. All right, now The strength of ionic and covalent bonds increases when the electronegativity difference increases. Oh. All right, the strength of the bonds increases when the change in electronegativity increases, the difference between them. All right, so if that's true, which are the strongest individual bonds and which are the weakest of those above? All right, so look in both the covalent and the ionic columns. All right, so I want you to take all of these and all of these and answer that question. And then fill this in, and then I want you to answer the summary question. So we will stop here on this video. Stop for first video. All right, so finish everything in that. All right, before the end of class. And then tomorrow we'll follow this these arrows and go up and start on the second topic. All right. Now, I hope you did really well. I hope you're working hard while I'm gone. Remember, as long as my husband is in the hospital in this way, I just can't come to school. It's too anxiety-provoking. So I will come as much as I can. And in the meantime, I really want you to learn. And I'll make videos so it still feels like we're together. I'm not abandoning you. All right? All right. Carry on.